Great. So our next speaker is from the Waveform working group, Professor Harald Pfeiffer. He leads the Max Planck Institute Gravitational Physics, a group in Max Planck Gravitational Physics Institute. And he's in the, of course, in LISA waveform modeling group. And he also was faculty of University of Toronto and CETA here a long time before he moved to Germany again. And so he has deep ties with Canadian physicists too. So we will hear his talk now. Harald, please go ahead whenever you're ready. I think you're muted. Yes.
Yes, I am. Thank you very much for inviting me to speak here. It's always good to be back in Canada, even if just virtually. So I'm here to present the waveform groups within LISA. There's actually two of them, and I'll get back to that later on. But the two of them are working very closely together. Just as a motivation for why waveforms are important, the waveforms underpin essentially all the extraction of science from the LISA mission. So it's this great mission, lots of cool technology, satellites flying around. But at the end of the day, similar to LIGO and Virgo, we need to know a great deal about the waveforms of the expected signals in order to extract the science. The three images here at the bottom of the page are from LIGO Virgo, because our colleagues there have the slight advantage that they already have data to analyze. So to detect signals, LIGO uses template banks. Something similar is going to happen for at least some signal types in LISA. Parameter estimation works by comparing the observed signal with the expected signals and plotting out the region of parameter space where the two are consistent with each other. And also testing general relativity and learning about fundamental physics and fundamental properties of gravity also requires precise knowledge of what the predictions of GR actually are, which then in turn will be translated into waveforms. However, while all of this works very well currently for LIGO and Virgo for the ground-based detectors, the task is much harder in LISA than currently for the ground-based gravitational wave detectors. There's three different reasons for this. One is that LISA sees much more diverse sources. There's novel types like supermassive black holes or extreme mass ratio inspirals. For all the types, the parameters can be much more extreme. For instance, for black holes, higher mass ratios, higher spins, more eccentricity. Also, quite a bit of the sources that LISA is going to see have significant higher signal-to-noise ratios than today. That's indicated in the lower right panel that shows the signal-to-noise ratio for supermassive black hole mergers. And you can see there's a significant region in parameter space where the SNR is 500 or 1,000 or even several thousand. Currently, gravitational wave detectors have to deal with signal-to-noise ratios of 20 or 30. And so increasing the signal-to-noise ratio by a factor of 100 implies that the waveforms being used to analyze these signals also should be more accurate by a factor of about 100 in order to avoid systematic biases. And finally, LISA has significantly more ambitious science goals than what's presently the case for the ground-based gravitational wave detectors. For instance, we aim to measure eccentricity of the various inspiraling sources to an absolute precision of about 0.001. And that is really scary because it actually also implies that for waveform purposes, waveform modeling purposes, we need to be able to predict the waveforms good enough that such minute changes are still visible and correctly represented in the waveforms. Hence, the primary goal and task of all the waveform efforts within the LISA collaboration is to ensure that the quality of the LISA science is not limited by our capability to solve Einstein's equations. It's a nice little sentence here, but let me actually split it up in a few different subtopics to give you some sense of the flavors of work that is happening within the waveform group. One way to split things is by the type of sources that are being considered and that waveforms are being required for. That starts from massive black hole binaries. So supermassive black holes of order 10 to the 6 solar masses merging with another supermassive black hole of about 10 to the 6 solar masses, give or take factors of 10. There are extreme mass ratio inspirals where a very small body, 5 to 10 solar masses, orbits 100,000 times around a supermassive black hole, leading to potentially utterly ridiculous trajectories like the one indicated in the top right part of the slide, because of the very tight coupling of the big black hole spin with the little black hole's orbital angular momentum. We have galactic binaries, 2 white dwarfs orbiting on timescales of 5 to 10 minutes. There are stellar origin black hole binaries that are first visible in LIGO, in LISA, at low frequencies, perhaps a month or a year or so before the very same system is visible in ground-based detectors during its merger phase. Transient sources, cosmic strings, other sources, things nobody has thought about, as well as going beyond general relativity and beyond standard model sources. Another way of slicing the waveform efforts is by the modeling approaches and tools being used, and there's also are quite varied. One needs numerical relativity to do the late inspirals of the binary black holes. One uses weak field approximations, post-Newtonian, post-Minkowskian for the early inspiral for systems far away from merger, including white dwarf binaries. Extreme mass ratio systems make use of the small mass ratio approximation, a perturbation theory where one body is a lot less massive than the other body. Effective on body models to put everything together, phenomenological models, waveform models, put all the information together and turn them into something usable for data analysis. All this needs to be combined with acceleration the waveform generation techniques, because the high fidelity first principle calculations are just too slow for any realistic data analysis. So at that front, surrogate modeling, reduced order modeling will be important, as well as hardware acceleration like GPUs. The headings I'm listing here, by the way, are directly coming from the waveform white paper, which I will also be mentioning later on. While I personally believe that general relativity is correct, I would be truly thrilled to find some signature of signals that go beyond general relativity or beyond the standard model. So there as well, the whole plethora of tools needs to be adopted to simulate theories beyond general GR, starting with numerical relativity, post-Newtonian, perturbation theory. The whole list again needs to be modified and generalized for those cases. And then there's also scientific fine print, which seems annoying and unnecessary, but which actually matters a great deal. We need to make sure that we know how accurate the various waveform models are needed. For instance, supermassive black hole binaries with a signal-to-noise ratio of several thousands, it's absolutely no deal at all to find these systems in the source, in the data stream. It's very easy to do fairly precise parameter estimation because the sources are so loud. But then there's the secondary restrictions that the very same data stream also includes the weaker sources below. And so one of the questions that arises is, how well do we need to be able to subtract the loud signals in order to reveal the weaker signals without any biases? We need to think about efficiency. And we also need to think about interfaces and data format requirements such that everything at the end of the day fits nicely together, both within waveforms and within the users of the waveforms in the data processing and the data challenges groups, as well as the other working groups like the fundamental physics and the astrophysics. So a lot of different aspects are going on here. Many of them interrelated and also interrelated to other pieces of the collaboration. I like this plot that Thomas plugged into his presentation, so I figured I'll show the same to point out where the waveforms sit in this big management diagram of LISA. And the waveforms are actually there twice. They were once as a working group at the very bottom in the blue layer, interfacing into the larger science community. But waveforms are integral enough that they form a part of the LISA science group, a work package group, with the actual deliverables for needed to deliver the LISA science in due time. So the waveform working group is the entry point for interested people. Presently has about 200 members. It's also presently preparing a white paper like the other working groups as well. It is chaired by a set of 4 very nice people, Detre Shoemaker, Martin van der Meent, Niels Warburton, Helvi Wittek, which cover the different areas of expertise and different geographies. And the Waveform Work Package Group is the subset of researchers who actually commit research time to LISA efforts and who are also bound to produce the deliverables needed for the LISA mission in due time. The work packages are roughly structured by source type, and the work package group is chaired by Leo Barak and myself. All of this is waveforms. All of us tend to be interested in the very same things, both pushing the capabilities of waveform calculations and, of course, the applications of the waveforms to do science with them. And therefore, there's a very strong overlap between both groups. Getting involved, well, one idea is the most obvious one is to join the Waveform Working Group. We have annual meetings that used to be in person, and hopefully soon next year will be in person again. There's a monthly Waveform Working Group call to learn more. And perhaps the most immediate opportunity to get involved is to actually read and give feedback on the Waveform Working Group white paper that is presently in its draft stage and will soon to be distributed within the wider working group and within the LISA science group. It gives an opportunity to learn what's going on, to immediately connect to other researchers in the working group, and also immediately an opportunity to feedback your own knowledge to the benefit of the working group. And of course, students and postdocs are particularly welcome to join as well, not just senior researchers. Thank you very much.
Thank you very much for a nice talk. So let's first thank our speaker. Great, so good information in this talk also. We have around 10 minutes for questions, a little bit more, of course. So again, feel free to post your questions here in Zoom so I can ask the speaker. I would like to ask also how much overlap is between the waveform group and the fundamental physics group, because it seems to me that there are lots of works that.
Yes, like Thomas before me, I would say that there's significant overlap, and right now the most immediate overlap is that we are presently figuring out how accurate the various waveform models need to be and what parts of parameter space they need to cover. And especially the parameter space question, of course, depends a lot on the astrophysical expectations. We need to make sure that we absolutely certainly can handle all the cases that are expected. And then beyond, there will be some trade-off between how hard a certain extension is as compared with how likely those things are supposed to happen. Then there's also overlaps with the, of course, with data processing, because we need to provide waveforms of sufficient accuracy to make all the data extraction possible, and also in a format and in speeds well enough to handle all the things there.
Okay, thank you. So there's another question. Actually, we have good number of questions here in the chat. So one question is that, is there any overlap with those computing waveforms for LIGO, Virgo, and pulsar timing measurements?
There's significant overlap with LIGO and Virgo. In fact, currently LISA is just using the LIGO and Virgo waveforms. And this is good for current day scoping out of events. However, both LISA as well as the third generation ground-based detectors have the difficulty that the future detectors need much more accurate waveforms. And so there is a joint effort already between LISA waveforms and LIGO third generation waveforms to join forces wherever possible. That's, for instance, the case for comparable mass binary black holes. It's also the case for intermediate mass binary black holes. Extreme mass ratio events aren't visible in LIGO ground-based detectors, and things like white dwarf binaries also aren't visible in ground-based detectors at all. So obviously there isn't any overlap.
Okay, great. Another question is, suppose I have a great idea for a new physics signal with an unusual gravitational waveform. Who should I talk to about its detectability?
That's an excellent question. And I think that is a cross-section somewhere between the astrophysics working group and the waveform working group. Finding out very early detectability studies is fairly straightforward. It boils down at the 0th order to compute the signal-to-noise ratio under the LISA noise curve. But then once this looks promising, there comes the more nitty-gritty detail to figure out how much this new signal overlaps with other sources, whether there are difficulties with distinguishing them, or whether there's different difficulties with searching for them. So some combination between waveform group, astrophysics group, and perhaps the LISA data challenges.
Very good. One more question, I think, regarding this. So the question is that, is there a mainstream set of modeling techniques that will be mainly used, or is it super variable? Are there any prospective techniques that the group is hoping to test out?
There's basically all the techniques that are known have to be used to make progress. It's the analytical waveform models for the early inspiraling. It's numerical relativity near merger. It's perturbation theory in extreme mass ratio limit. All of that needs to be combined into coherent waveform models with EOB and phenom. And then we also are currently using and exploring every single type of acceleration technique that has been developed in mathematical analysis, surrogate models, reduced order models, GPUs, artificial intelligence. So I think the basic set of tools is pretty much fixed because they're so very well developed, but especially in terms of efficiency, there's so much flux and so many new results currently coming in, also motivated by LIGO, and perhaps even more so needed for LISA and third generation ground-based detectors. But on that front, there's still a lot of flux.
Okay, thank you. We have one more logistic / structural question. Are there people appointed to liaison between the working groups?
Not formally to my knowledge so far. The working groups and the work package groups liaise in their own leaders telecons anyway, but quite a few members are actually people are members of several groups depending on interests, and those then also naturally transmit information. But it is certainly a point to think about in the future, whether we would want more formal cross collaboration and coordination between the different working groups. It's a fairly complicated structure that Lisa has been setting up over the years. Oh, and I'm just stopped my screen share, too bad. I was hoping to go back to the slide.
Yeah, you can go ahead and
where with the organogram.
So where you want to share the screen again?
Yes, I'm back on my way.
Okay.
But while I do this, feel free to already post whatever the next question is.
So the next question is that what aspect of developing quality waveforms are you most worried about getting done before LISA launches?
Intermediate mass ratio systems. 10 to the mass ratio of about 100 to 10 to the 4, thereabouts. That's the mass ratio regime, or perhaps even down to 10, where numerical relativity is not very useful because the mass ratio is too extreme, where perturbation theory is not yet too useful because the mass ratio isn't extreme enough, and where the big black hole's angular momentum is so dominating that precession is truly extreme, and the systems can also be highly eccentric.
Okay. So there's another question, I think maybe by a student, maybe. Hello, could you suggest some good resources to study the waveform models from binary?
Binary white dwarfs.
Yes.
That's basically, my understanding is that basically post-Newtonian theory might be good enough there. I'm not a white dwarf expert, so I actually don't know. There's a lot of post-Newtonian theory there. I'm hesitant to suggest Luc Blochet's big review of post-Newtonian theory in Living Reviews because it's too complicated. However, I'm not expert enough to know whether there are interesting astrophysical complications going on, like resonances within the white dwarfs that impact the waveforms. Could be, but I simply don't know.
Okay, so there you have your answer. Another question here is that where can this where can this white paper be found?
It cannot be found just yet. There's various subsets within the waveform working group of people who are working on the various chapters. And right now, the integration is under process to prepare a first complete draft. Once this draft is ready, which should be in about a month or so, timescale of order months, then it will first be shared within the waveform working group for feedback, and then subsequently in the bigger LISA science working group. So to get to the white paper, you first need to join, you presently need to join the consortium as an associate member, and then you can contribute there. Later, of course, once the thing is finished, then it will be made publicly available, but not right now.
Okay, very good. So again, if you have any questions, you can post them here. We have maybe time for 1 or 2 good questions. And in the meanwhile, people are actually thanking you on the chat too. So it seems that
thanks for that. Yeah, thank you for all the interest and all the good questions along the way.